Imagine a coin that never lands. It hangs in the air, spinning, until you tell it how to land. Ask, heads or tails along this direction, and only then does it snap to an answer. Ask along the same way, and you get the same result, but change the direction of the question, and the coin decides again. And that's the feel of quantum spin. Despite the name, nothing is literally rolling. If an electron were a tiny ball, it would need to rotate faster than light to match what we measure. So spin is actually just intrinsic angular momentum, a built-in property just like charge or mass, and it only shows itself when we ask along an axis. So how do we ask? With a magnet whose field has a slight slope. Here's what I mean. In the 1920s, two scientists Stern and Gerlach sent neutral silver atoms through such a field. If spin were ordinary orientation, the beam would smear across the screen. Instead, it split into two crisp dots. Along that axis, each atom answered either up or down. That's a fingerprint of a spin half particle. There are two possible outcomes and never in between. But here's the twist. Get Z up, then rotate your apparatus and ask along the x-axis. You'll cleanly get x up or x down, but your old Z answer is no longer guaranteed. In quantum mechanics, we say that these questions don't commute. Measuring along the x-axis projects the spin into an x state and erases the previous Z definiteness. But why should we care about spin? Electrons are spin-half fermions and obey the Pauli exclusion rule. No two can share the exact same quantum seat. That single principle builds the periodic table, chemical bonds, and the solidity of everything. So an electron's spin isn't some spinning top. It's a coin that only lands when you ask, and only for the direction you choose. In the quantum world, the question shapes the answer, and from that small rule, we get the blueprint of matter itself.